Behind me is a function that solved a difficult problem in history. However, before we start toying around with this function, we need to explore the problem, right? So let's do that. Take the positive integer 4 as an example. I'm going to ask you, how many ways can we break up 4 as the sum of smaller positive integers? Okay, we'll count 4 as its own, so this is one way. However, if it's not this, then how many ways can we break up 4 as the sum of smaller positive integers? Well, we have 1 plus 3. And here's the thing. We'll only consider a way different if it contains different positive integers. So for instance, we have 3 plus 1, right? However, 3 plus 1 is considered the same as 1 plus 3 because this over here is just this, but 1 and 3 are swapped around, right? It still contains the same positive integers, so this is not considered different from this. So we don't care about the order of the numbers in the sum. We also have 2 plus 2. This is considered different. We also have 1 plus 1 plus 2. And finally, we have 1 plus 1 plus 1 plus 1. Thus, there are 5 ways. Now, each of these ways, they are called partitions. So this is a term that we can use formally. And specifically, we have partitions of 4 right on our left. And each individual number in the partition, like this 3 here, this is called a part of the partition. Now, here's the problem. Given any positive integer n, how many partitions of n are there? Well, you might try to find a pattern with the number of partitions in 4, 5, 6, and so on, but the pattern isn't really obvious. And even if there was a pattern, it's going to be kind of hard to prove that this pattern holds on and onward, right? So we can actually use a more clever algorithm to solve this problem. In this video, I'm going to be introducing you to generating functions. I'm going to be writing that on the board for you. So generating functions. And while I write, I'm going to talk. Generating functions might sound a little bit fancy, might not to you. However, regardless, this is a very clever algorithm to use in counting problems. The idea of a generating function is that we create a function, and when we expand it, the coefficients of each term will give us a counting number. And all we have to do to get the answer to a particular counting problem is to read off that coefficient. Still, that might sound a little bit weird, so we're going to go into a very simple example. Suppose we have person 1, person 2, and finally, person 3. Suppose that person 3 will be collecting money from person 1 and person 2. Now, person 1 can contribute either $0 or $1. Person 2 can contribute $0 or $2. So not $1, only 0 or 2. Now, how many different possible total values can person 3 receive? So maybe person 1 and person 2 will contribute nothing at all, so person 3 gets 0. But maybe person 1 and person 2 contributes $1 and $2 respectively, so person 3 gets $3. So how many different possible sums can person 3 get? Well, consider this. We can model person 1's outcomes as 1 plus x to the 1. Now you might be thinking, whoa, where did this come from? What is x even representing here? Well, if we rewrite 1 as x to the 0, notice what we're doing. We're placing the possible outcomes from person 1, so either 0 or 1, as the exponents on a placeholder variable. Now, the placeholder variable isn't important. We can use y, z, a, b, c, d, right? That's not important. But the point is that we're placing the outcomes as the exponents on a placeholder variable. We can similarly do so for person 2. His outcomes will be modeled by 1 plus x squared this time, right? And here's the idea. When we multiply these two polynomials together, notice what happens. The exponents on them add. So for example, let's just say person 1 decided to contribute $1 and no dollars. I've underlined. So person 1 contributes no dollars, representing the 1, and person 2 contributes $2, representing the x squared. When we multiply the polynomial, when we multiply 1 times x squared in the expansion, right? Then we would be doing x to the 0 times x squared. Now, because we're multiplying, the exponents add. And our resulting exponent in this case is 2. But remember, 0 and 2 were the outcomes from person 1 and person 2, right? So when they added, the resulting exponent represents a possible sum that person 3 could receive. In this case, $2. Person 3 can receive $2. It's a possible value. So, taking another example, let's say that person 1 decided to contribute $1. Then, when you multiply this, you would do x to the 1 times x squared. Adding the exponents gets us x to the 3. But because it was added from the exponents, and the exponents represented a possible outcome from person 1 and person 2, $3 in this case is also possible for person 3 to receive. So notice that this is the idea. When we place the outcomes as the exponents on a placeholder variable, and when we multiply polynomials, the exponents will add corresponding to a possible sum. Now when we multiply this entire thing out, we get 1 plus x squared plus x cubed. So we can see that 1 is x to the 0. So we can see that one possible sum is $0, or $1, or $2, or $3. So there are 4 possible sums that person 3 could receive. Now, let's do a more complicated problem. Let's say that instead of only having 2 persons or 2 people donate money, let's say that person 3 decided to give money as well. So person 3 will give $0 or $3, and there's also a person 4 who would give $0 or $4. Right? Now, let's just say that there's a person 5 somewhere here who will be collecting money from person 1, 2, 3, and 4. So how many different possible sums or total values of money can person 5 receive? Well, like we did before, we'll model person 1's outcome with the polynomial 1 plus x to the 1, right? Now person 2, his outcomes can be modeled by 1 plus x squared. And similarly for person 3 and person 4, it would be 1 plus x to the 3 times 1 plus x to the 4. And because this is a bit more complicated, we'll run through another example. Let's say person 1 decided to contribute $1, person 2 decided to contribute nothing, person 3 and person 4 decided to contribute a positive amount, $3 and $4. So in the expansion, when you end up multiplying all these out, we have x to the 1 times x to the 0 times x to the 3 times x to the 4. Their exponents would add, giving x to the 8. So thus, we see that 8 is a possible sum that person 5 could receive. Now, let's actually multiply this entire polynomial out to see what we can get. Now, multiplying isn't too hard. If a bit, it might be tedious, right? So we would get 1 plus x squared plus 2x to the 3 times plus 2x to the 4 plus 2x to the 5 plus 2x to the 6, right? And then plus 2x to the 7 plus x to the 8 plus x to the 9 plus x to the 10. Now, this one's a bit different from the one that we had before. There are coefficients of 2. So, do these coefficients have any relevant meaning behind them? Well, a good question to ask is, why is there a 2 at all? Well, it's because when you multiply this entire polynomial out, there were 2 x to the 5 terms in the expansion. So naturally, we would just combine them and we get a coefficient of 2. But where did these x to the 5 terms come from? The exponent of 5 came from as a result of multiplying these terms out and the exponents adding up to 5. So in this case, we could have had x to the 1 times x to the 4, right? Or we could have had x squared times x cubed, right? So because each of these x to the 5s represent one way to get a $5 sum, right? So 1 and 4, maybe person 1 contributes 1 and person 4 contributes 4 and person 2 and 3 contribute nothing. That would add up to x to the $5. And similarly with person 2 and person 3 contributing 2 and 3 and these two contributing nothing. That would also get you 5. So when we add them together, the coefficient is really telling us how many ways are there to get a sum of $5, right? And similarly, there are also two ways, right? So basically, there are two ways to get a sum of $5. But there are also two ways to get a sum of $3, $4, $6, and $7. So that's what the coefficients are telling you. You might have also guessed that a coefficient of 1 means that there's only one way to get a sum of, say, $1 or $2 or $8, right? Or $9, or even $10. So, and by the way, there are 11 possible sums, so ranging from $0 to $10. So that is the idea behind generating functions. I hope I just added a new counting tool to your toolbox. Let's go back to our original problem. How many partitions are there for a given positive integer n? Now, we've just seen how generating functions can be quite useful in determining the number of possible sums, as well as how many ways are there to achieve a particular sum. However, in this case, we kind of need to first go back to what a partition was to be able to use generating functions effectively here. So recall that a partition was basically a way to write n as the sum of smaller positive integers. So every single partition will contain some number of 1s, some number of 2s, some number of 3s, and so on and so forth. So for instance, the partition of 4, where we had this one contained two number of 1s, right? 2 1s, I should say. 2 1s and only 1 2. And how many 3s does it contain? 0. We'll count 0 as another option, right? But the point is that every partition will contain some number of 1s, some number of 2s, some number of any number, right? It could be 0. So we'll actually write n as this. N is equal to, suppose there are A1 1s. Then the sum of all of those A1 1s is A1 times 1, right? And let's say that there are A2 2s. Then the sum of all of those 2s is A2 times 2. And we also have A3 times 3, because there's A3 3s, right? And we'll go all the way until an times n, where an is the number of n's in the partition. Now I know that an can only either be 0 or 1, but we're going to make this as general as possible and just write an. So, and in addition to that, by the way, we'll actually go up all the way to infinity. So an plus 1 times n plus 1. Now I know that an plus 1 has to be 0, right? But we're still going to make it as general as possible. We're just going to leave it as an plus 1, an plus 2, so on and so forth, to make this expression general. So this goes on forever. Now, all this is finding the number of solutions of a1, a2, a3, all the way to an, and so on and so forth that satisfy this equation. That will give us a partition. Now, that's still kind of hard to do, so let's go ahead and zoom in to one particular term of the partition, a1 times 1. Now, how many possible values are there for a1 times 1? Well, a1 times 1, we can model its possible values as a generating function, or a polynomial. Basically, a1 times 1 can be 0. If a1 is 0, then that's 0. So one possible outcome we can write as x to the 0, which is just 1. Or when a1 is 1, it is 1 times 1 equals to 1. So another possible outcome is x to the 1. It can also be 2, right? And 3, and so on and so forth. Basically any non-negative integer. Now, consider a2 times 2. How many possible values are there for a2 times 2? This one's a bit different because there's a times 2. Therefore, this entire term must be even, right? It's a multiple of 2. So, we can model this with the polynomial x to the 0, 1. Or we have x squared this time, and x to the 4. And it's basically any even number for the exponents. Now, a3 times 3, again, this thing only can be multiples of 3, right? So we can model this with the polynomial 1 plus x cubed plus x to the 6, basically any multiple of 3. And an times n, this over here, its possible values, so dot dot dot, and then times, its possible values are 0, so 1, or x to the n, right? Or x to the 2n, plus x to the 3n, plus so on and so forth. It must be multiples of n, right? Because there's literally a times n to this thing. Therefore, this is its generating function. And it goes on, so on and so forth. So we have n plus 1, n plus 2, and it just goes on, right? So I'll write dot, dot, dot to indicate that. Now, this is our generating function. When we multiply all of these together, the exponents will add, and the coefficient of x to some exponent will tell us how many ways are there to get a sum of that exponent, right? However, this is an infinite series. I mean, these are infinite polynomials, if you'd like to call them. They're more formally called power series. And I'm not really comfortable with my generating function being infinite polynomials multiplied together. I mean, like, how do we even expand infinite terms? Well, we can thankfully condense these infinite power series. If you remember, what is the sum of a geometric series? Well, okay, sorry, oops. Well, let S be equal to a geometric series, 1 plus x squared plus x cubed plus so on and so forth. Now, the common ratio is x because you multiply x by the previous term to get to the next term, right? Now, consider this. Multiply both sides of the equation by x. So we have x times s is equal to 1 times x is x times x is x squared, x times x squared is x cubed, and so on and so forth. Now here's the idea. When we subtract the equation, so when we do s minus x times s, well, on this side we just have this. However, on this side of the equation, notice that the x's and x squares and x cubes, all of them actually cancel out. And it's an infinite series, so it just cancels out forever. The only uncancelled term is 1. Here we may factor out s. And finally, divide both sides by 1 minus x to achieve our formula. So this expression s equals to 1 plus x squared and so on and so forth. This has a very neat formula. It's just 1 over 1 minus x. One thing I should note, however, is that this formula is only valid if negative 1 is smaller than x smaller than 1. The reason being is because if you plug in x is equal to 1, first of all, 1 minus 1 is 0, and denominators of 0 make no sense. But furthermore, plug in 1 into this original expression, right? So 1 plus x squared plus x cubed. I'll write this out so that you don't see the crossed out version. Consider plugging in 1 for x into this series. You get 1 plus 1 plus 1, infinite ones. That shoots off to infinity. So what is the meaning of this formula at all? And furthermore, plug in something like 2. Well, that's 1 plus 2 squared plus 2 cubed infinitely. That's going to go to infinity. But this formula will tell us it's negative 1, right? So this formula is actually only locally correct. There's a certain range for which you can use this formula. So you might be wondering, are you telling me to replace this with this then? Yes. And you might be wondering, okay, well, isn't there a restriction? Well, here's the thing. We don't actually care about what the placeholder variable is. We'll just to our heart's content, make it so that x is satisfying this condition so that we can make this substitution into this. Now, I know you might still be wondering, is that actually legal? Is that okay to actually do? Well, yes, but the proof of that is going to be a little bit more rigorous. I'm going to have to include more rigorous details in order to prove that. But for now, just think about it like this. We don't care what the value of x is, so we can just set it so that it satisfies this condition. So that is going to be our condensed form. We can write our generating function as this part as 1 over 1 minus x. And this part over here, well, this is the same thing, except the common ratio is x squared, right? So instead of x down here, we should have 1 over 1 minus x squared. And this one over here, you have, well, 1 over 1 minus x cubed. And this just goes on, so on and so forth, until here, right? We have 1 over 1 minus x to the n then, right? And actually, we don't stop there. We had an infinite product, so it just goes on forever and ever. So yeah, we have an infinite product, but the product doesn't look like we're multiplying infinite power series anymore, so that's better. So now this is our generating function, and I'd actually be quite happy with this. I'd actually accept this as an answer for what is the generating function. I'm fine with this. However, you might have noticed, and once I erase all of this, you might have noticed that it's still an infinite product. And infinite products, well, that's up to you to decide whether if you like to look at them or not. You'll notice that at the top, I decided to use this weird notation. What is this? Well, it's basically a way of writing infinite products so that they don't look like infinite products. So I'll teach you this notation if you're interested. Basically, this notation is the pi notation. You might have guessed that it's a pi notation because of how it looks like, right? And just to let you know, this has nothing to do with the lowercase pi, which is approximately equal to 3.14, right? This is the more famous pi. This has nothing to do with this. So what is this symbol doing then? Well, it's basically a way to shorten or condense products of long length, especially if they're infinite, right? So let's take this example. Pi, and then we have the base value I is equal to 1 and going up to 5. Basically what this means that if I give you an expression such as I cubed, this is telling you find the product of I cubed, where I iterates from 0, 1, 2, 3, and 5, right? Because 5 is the upper bound. So this would be 1 cubed times 2 cubed times 3 cubed times 4 cubed times 5 cubed. Notice that I is changing from 1, 2, 3, 4, 5. And the upper bound is 5. So this is a way to basically denote iterative products. And if we had something like pi, and the base value is I equals to 1, and here we had an infinite symbol up here, then this would basically, and let's say our expression is this, by the way. And if we were to evaluate this product, or rather write it out, our expression would be 1 over 1 times 1 over 2 times 1 over 3 times 1 over 4, and going on forever, because it's an infinite product. So this is a way we can denote infinite products without having to write it out like this. Likewise, we can condense this into a pi notation. We know it's a product, so start by writing pi, obviously, right? Now, because it's an infinite product, we would obviously expect the upper bound to go on to infinity. And the base value, think about what changes in the product. The exponent on x changes, right? With x starting at x to the 1, right? So it seems wise that we should set the base value k equals to 1. I and k are just placeholder variables, and they're of no meaning. You can use m, I, n, right? As long as it's not a variable in the product, however. So it wouldn't be wise for me to use x is equal to 1. Otherwise, I mean, x is already used here. It will create confusion. But k is totally acceptable. And now we write our expression. Our expression is 1 over 1 minus x to the k. And basically, k will iterate from 1, 2, 3, 4, and so on infinitely. And this will change this expression over and over and multiply all of them together. So this is the condensed form of our generating function. I hope you found this video interesting, and if you did, definitely do consider subscribing and dropping a like. Thank you very much. See you next time.